Hello again. Today we're talking about valence electrons and a little bit about ionic compounds. So, valence electrons are electrons that are involved in chemical bonds. This is the best possible definition. Often you will find a definition that valence electrons are electrons of the last energy level, but that's not technically correct because that's only correct for s elements and for p elements. Because for transition metals, for d elements, and special for f elements, we don't even know what's the last energy level. So valence electrons don't do not necessarily mean just the electrons in the last energy level. But this definition works best. So those are the electrons that are involved in chemical bonds, not only in ionic compounds. So valence electrons are important for covalent compounds too, and we will talk more about that in the next unit. For now, we're mostly considering just ionic compounds just because they're simpler to just learn this first. So, ionic compounds are made of ions, and a stable ion is an ion that has a full energy level. So, the position of S and P elements in the periodic table can tell us what its stable ion is. How? Well, lithium is in group one. So it has one electron, the last energy level. So if it loses that one electron, then the energy level under is full, which means that that's a stable ion. And then oxygen is in group six. Remember, we don't call this 16. We call these groups one, two, three, four, five, six, seven, and 8. That's mostly how we call them in chemistry. Nobody really says group 16. So oxygen is group six, so it means it has six electrons in the last energy level. So the easiest way for it to get a full energy level is to gain two electrons, and then it's going to be oxygen 2 minus because it's got two extra electrons, right? And then it's going to have 8. So these here are closer to zero, and then the energy level under is going to be full. So these here lose electrons, group 3 also. Group 4 has 4 electrons, so it can gain 4 or lose 4 in order to have a full energy level, right? So, and then these group 5, 6, and 7, they're more likely to gain electrons. This doesn't always happen, as we discussed, as you will see in our previous courses, is like nitrogen could be plus 5 too. Chlorine for that matter can be plus 7. But most likely, this is how they get to a stable configuration. And that configuration is often not called, we don't say how to get to 8. We say that the stable ions, atoms gain or lose valence electrons to reach the nearest noble gas configuration. Why the nearest noble gas configuration? Well, if you look at lithium, has 3 electrons. So it's 1s2, 2s1. So it loses 1 electron, becomes lithium 1 plus. And now it has how many electrons? Now it's just 1s2. That's not 8. So basically, it's best to say that ions are formed in order, it's always in order to get to a stable configuration. But that stable configuration is not always 8. That stable configuration is a full energy level configuration. Or you can say it like here, the nearest noble gas configuration. So basically, lithium 1 plus is 1s2, which is just a configuration of helium. And chlorine, you add 2 electrons. Actually, you add 1 electron. That's the electron configuration of argon. So you're going to see this definition where they connect this to noble gases. But again, that just means a full energy level. And also don't get confused because, this is 1 plus and 2 plus and 3 plus. Many chemists will just say plus 1 and not 1 plus. But for ions, by convention, we should say the number first and the charge second. So, just bear that in mind. You can see a bit of a better overview of this here about how this works. Now, when we are making an ionic compound, we have to take care that the sum of all the atoms in that compound is 0. So if I were to ask you to make me a compound from aluminum and oxygen, and this is group 13 or actual group 3, right? and it's 3 plus. Oxygen is group 6, 16, so 2 minus. So how am I to merge this and in order to get for the whole thing to be 0? Well, if I multiply aluminum by 2, that this side becomes plus 6, right? And I multiply oxygen by 3, and then this side becomes minus 6. You're only allowed, basically, I mean, you know this, to multiply. You're not allowed to, have half of this and like 2/3 and whatever. So uh, you will see that, I mean, first of all, for ionic compounds, basically only group 1 and 2 with group 6 and 7 will form actual ionic compounds. So it will most likely the elements from group 3 and 5 will not really form ionic compounds. So ionic compounds depend on the electronegativity difference, but they want you to learn valence electrons here. So don't get confused that they involve all the groups here when explaining valence electrons. So it's not necessarily very much connected to ionic compounds. Now, also bear in mind that ionic compounds are lattices. So let's say I have NaCl. NaCl is not just one Na and one Cl. It's a lattice that looks like this. So this is a sodium chloride, so NaCl type lattice. Remember, it's 3D, and every positive ion is surrounded by six negative ones, and vice versa. And yeah, they're never paired. And most of the structures look like this. If the ions are 1 to 1, it's going to look like this. So NaCl will look like this, and MgO will look like this. But if it's MgCl2, it will look a bit different, as you will see again later when we talk about ionic compounds. Now, we have a bunch of examples here. You will see the questions in this chapter also include questions from the previous chapter, and a lot of questions from this unit. So it's not really possible to do all of them, but there are some good ones right here. So strontium sits in group 2. Determine the number of valence electron in a neutral strontium atom and the charge of the ion it forms, and justify the ion using electron configuration. So this is a fairly simple one, since strontium is in group 2. So it has 2 valence electrons, and it's easier for it to release 2 than to gain 6. And then that means that the stable ion is Sr2 plus, and that's the electron configuration of krypton, of the noble gas krypton. Ooh, Superman. Potassium reacts with sulfur. Predict the ions each form and write the formula of the neutral ionic compound. So potassium is in group 1, right? So it will be +1 or 1 plus actually. And sulfur is group 6, so it's going to gain 2 electrons and become S2 minus. So I'm going to need 2 potassiums to make this neutral. So it's going to be K2S. Barium. Barium is group 2. Reacts with chlorine to form BaCO2. Okay, using the periodic table, predict the formula of the compound that radium forms with iodine and explain why the two formulas share a pattern. So right now I need to look at where radium is, and I don't want to switch to the periodic table to confuse you, but radium is also group 2. So if it's BaCl2, it's logical that it's also going to be RiCl2 or RiI2. So because Ba and radium are in the same group, and chlorine and the other, I mean, group 7 elements are obviously in the same group, so they're always going to form equivalent compounds, similar compounds like this. You will see a lot of questions like this in the actual AP questions. Rank the group 1 metals lithium, sodium, potassium from least to most reactive, and justify the order in terms of how the nucleus holds the valence electron. So this is a good question, and one connected to chapter 1.7. So we've got lithium, we got sodium, we got potassium, right? So lithium is the first period, and then sodium is under it, and potassium is under it. So obviously, for potassium, the electron is going to be more far away. So these are in group one. In order to get to the stable ion configuration, they want to release an electron. So which electron is the easiest to release? The one which is the most far away. So basically, potassium will be the most reactive because it's the easiest to release the electron. So again, here is a little something that you will also practice in the next chapter. So in order for something to react, things react in order to reach a stable electron configuration. So what is the easiest to react is that atom that can the most easily get to the stable electron configuration. And in this case, that will require for all of these three to release the electron. And which one is the easiest to release? Is potassium, and then sodium, and then lithium. Obviously, a student notices that a non-metal bonds with fluorine. The number of fluorine atoms often equals 8 minus the non-metal's valence electron count. Use this idea to predict the formula for the compound of nitrogen with fluorine and state the reasoning behind the pattern. Again, this looks a little bit weird. There's a lot of questions like this in AP. They just want you to use Bayes logic here. So basically, it says a non-metal bonds with fluorine. The number of fluorines is 8 minus the non-metal's valence count, right? So for carbon, that's going to be 8 minus 4. That's going to be 4. So it's going to be Ca4. For nitrogen's valence electrons are 5. So that's going to be 8 minus 5, 3. So NF3, right? For oxygen, 6. So that's going to be OF2. So, I mean, you can see the logic. It looks pretty weird, but they just want you to apply it. Three ionic solids are built from similarly sized ions: sodium fluoride, magnesium oxide, and sodium chloride. Rank them by lattice energy from lowest to highest and explain using Coulomb's law. Okay, I put this in on purpose. This is also something that you will do in the second unit, but let's see if we can make a leap of logic here. So we've got sodium fluoride, we've got magnesium chloride, magnesium oxide, sorry, and sodium chloride, and rank the lattice energy. So which one of these lattice energy depends on the bond between these atoms? So which bond is the strongest? So magnesium and oxygen are +2 and -2, while both NaCl and NaF are +1, -1. So a bigger charge always wins in terms of which bond is stronger. Why? Because Coulomb's law depends on charge. So if the charge is doubled, the energy of that bond, and in this case, the lattice energy is just going to be much higher. So MgO will have much higher lattice energy than NaF and NaCl. But if we are comparing NaCl and NaF, the only difference is that NaF is in period 2 and NaCl is in period 3. So NaF is much smaller but has the same charge of -1. So that means that you've got Cl and F, they're both -1, but F is much smaller. This is called effective charge, not nuclear in this case, just effective charge. So it's a smaller ion with the same charge, type and number of charge as a bigger ion. So we got F minus like this, and we got Cl minus like this. So F minus in this case is going to be stronger. It's going to form a stronger ionic bond because of its smaller size and the same number of charges. So MgO stronger than NaF and then NaCl. Okay, practice and let me know if you need any help.